Tell you what, everything we just went through, why don't we look at it on the overall refinery block flow diagram, just so we understand what we just went through, where the FCC fits in a whole refinery. Basically, it's the bottoms off the crude unit, and then it's the side streams off the bottom. The very bottom typically will go to a coker or somewhere else. There's a limit, as we said, there's a limit to what this can take. In straight form, I mean, it's only like, well, what was the number we had? I guess we can look it up. Yeah, about 0.1 to 0.4 CCR. We make a resid out of it, we can go all the way up to 7% CCR. But still, you can't put the very bottom through here, just coke up too fast and burn so much coke it'll get so hot and you know, can't handle it. So anyway, you might hydrotreat it ahead of time to make it run better. And what else can we do? And a coker, of course, now some of the side streams coming off the coker, they'll go back to the cat and get processed into gasoline. And as far as some of the fuels that we took off the cat, fuel oil, which hardly anybody can burn anymore, but the gasoline's the main one, and then that LCO, a lot of times they'll go to a hydrocracker or else maybe a diesel hydrotreater. Where's the diesel hydrotreater? Right here. Okay, sometimes it'll go up here. So anyway, that's how the FCC fits in. Now what we're going to do next is those olefins, those light olefins, C4s, even C5s. The C4 what we call butylenes, and the C3 would be propylene. And they can go to units that make gasoline. And Chevron at El Segundo is even feeding the C5 olefins to the alky unit. And that's what we're going to do next. Now actually these olefins have decent octane by themselves, but they're too light. They create too much vapor pressure, and that's another thing that's being regulated in gasoline is vapor pressure. And that's used to be you had an open gas tank, and now you have a pressurized gas tank to keep the light ends from getting out in the air. So they're limiting how many light ends you can put in gasoline now. So that's one reason why these are great units. They take a C4 and make a C8 out of it, so much less volatile and good octane also. Let's see, anything else to say here? If we end up with time, another unit I'll get into is the cat reformer. See, this makes gasoline itself. It makes the olefins, which make more gasoline, and the other major gasoline maker is the reformer, and that takes basically naphtha off the crude unit and sometimes off a hydrocracker also, and can even come off a coker sometimes, but into a reformer. Now, it makes aromatic gasoline. This is aromatic and olefinic. Now, this gasoline here off an alky unit is isoparaffinic gasoline. So that's the ways you make octane: isoparaffins, aromatics, or olefins. And this one, and this is the favored gasoline, definitely. If you can make 100% alkylate, that's all you had for gasoline. That's what the AQMD would like, the Air Quality District. The isoparaffins don't burn quite as hot as the aromatics, don't make as much soot. They're usually lower in sulfur and lower in olefins. Olefins they consider react in the atmosphere to make smog, so there's something wrong with about everything we make, so except the alkylate, it's about the perfect gasoline. I was in on a strike in 1980 at Tosco up in the Bay Area, and we were filling our cars up out of the alkylate tank, pure alkylate in the car, you know. I had 11-to-1 compression forward, and it knocked on everything, but it didn't knock on that. So it's about the best you can get. Okay, like I say, we might get into reforming. That's another way of making octane. And so, okay, back to where we were now. Let's see. Okay, alkylation. Okay. There's actually another unit called polymerization, which isn't used so much anymore, but now we have a different process that we're going to cover in refining. It's most of the processes were desulfurization or cracking processes. This is more like a chemical process. You basically take two C4s and fuse them together and make a C8. The C4s are too light to put much in gasoline, but the C8's perfect. That's about what gasoline is. C7 to C9 is about where gasoline sits in the organic hierarchy. So once again, we'll get into the definitions and a little chemistry and type of feeds and contaminants in the feed. Now here, the catalyst in alkylation is plain old acid, and even with a lot of these fixed bed catalysts, there'll be a solid catalyst with acid impregnated on it. In this particular case, they just plain add acid straight in. Sulfuric acid or hydrofluoric acid are the two main catalysts for this reaction. And it's a liquid phase reaction. These other ones were real high temperature. You vaporized everything and then had a solid catalyst. In this case, you're mixing two liquids in the presence of acid, so it's a liquid phase reaction. No particulate catalyst to worry about. And let's see, we'll get into a couple of different alkylation processes, flow diagrams and the variables, and actually I probably won't get into the poly unit, but if I have time in the end, we'll get into gasoline blending, how you take all these different gasoline streams together and how you blend them to make what you put in your car. Okay, I guess, let's see now. Is that big enough to see, or do I need to expand it? It's not? Okay, so was that one there? Huh? Okay. Anyway, then we'll go to the next one, what we got here. Let's get into some definitions. And the purpose is to create a high-octane mixture of isoparaffin molecules, basically going from C4 to C7, C8, even C9 when you put C5s in there. So you fuse together, dimerize basically, isobutane and mixed butylenes, or propylene, or amylene, which is C5. So the product is in the gasoline boiling range and used in motor or aviation gasoline. Used to be what they put in the planes, the propeller planes. So they need real high octane there. What kind of feeds? As we said, coming off the cat cracker, mixed C3 and C4 olefin stream, iso and normal. From the FCC. Sometimes the coker creates some olefins too, so you'll feed those to the alkylation unit also. FCC feed is much better than the coker feed though, much higher butylene content and propylene content. C4 gives the best alkylate, C3 is decent, but now on the Gulf Coast, where all the petrochemicals are, we don't have many petrochemicals around here in California. They won't put that in alkylate. They'll make polypropylene out of it. There's a lot of petrochemical plants down there, so it'll recover your propylene and give it to a plastic maker. And now, even among the C4 butylenes, there's 3 or 4 different isomers, and the best is 2-butylene. And actually, they have a little process you can tack onto the front of alkylation that will maximize the amount of that. And so I'll get into that a little bit. Hydroisomerization. Now, the IC4, the isobutane you need, can come from a hydrocracker and the crude unit, a lot of different places. And what products do we get? IC5, IC9, basically IC7 to IC9 or 10. And since it's isomerized, has branch chains in it, it's much better octane than straight chain would be. Remember, 0 octane is defined as normal heptane. Now, isoheptane, on the other hand, has much higher octane. So isomerizing will definitely get you more octane. So, okay. Now the product stream then will have about 50% iso C8s typically, and some iso C7s, and even some iso C9s. The preferred one is the C8 trimethylpentane, TMP. It has a couple of isomers too, the iso C8, but one of them's called isooctane, and that's the basis for the 100 octane on the octane scale. The particular molecule isooctane is defined as 100 octane. And all you do with an octane engine is it's a comparison engine. You'll have isooctane and you'll run it in one engine, and then you'll take the fuel you want to measure the octane of it, and you'll run it in the engine side by side, and you'll compare it to isooctane. So that's what octane is. It's really just a comparison process to some standard fuels. Those standards being 0 for normal heptane and 100 for isooctane. Okay, what do we got next here? So a little more on definitions. The reaction, acid catalyzed, as I mentioned, exothermic. So we have to remove some heat. And conducted at a low temperature, not like these 950s and 1,000 degrees, 40 to 50 degrees, colder than ambient for when the sulfuric acid catalyst is used. Now this HF catalyst is actually somewhere more like 80 or 90 degrees F, so it doesn't require as much refrigeration. But now sulfuric acid, it's about 98%, 2% water. It's immiscible with this oil, so one of the things you have to do is hammer them together with a mixer, force them to mix, and in order to react. Now, one way to increase the amount of alkylate gasoline product is you maintain a big excess of isobutane, typically 10 to 1 or something. So there'll be a stream spinning around of isobutane, recycled isobutane, and so we'll show that when we get to the flow diagram. This excess isobutane inhibits polymerization reactions. We're putting two together, and under certain conditions more will want to go together. It'll make a polymer. I mean, 2 will go, 4 will go together, and pretty soon you'll have plastic. So this excess isobutane prevents this polymerization reaction. We want gasoline, not plastic. Some people want plastic, and that's a different plant. They'll do different things. Okay, catalyst, like I say, sulfuric and hydrofluoric. Now, the catalyst presumably does not react in any reaction, but in the real world it does to a small extent. So you'll get some organic sludge, acid sludge. Call it red oil because it's red. And it's a degradation product. And so you'll have to pull out some spent acid, send it back to an acid plant, and it'll be regenerated. So, and typically that'll be about 0.2 to 0.4 pounds for every gallon. And it's one of the major operating costs of alkylation is having to regenerate acid. So, okay, I have a better, see now, I have a better one for this. Manipulating these. Okay, all right, we did that one already now. Okay. Okay, now what we want is AlkyChem. Okay, so here's the basic reactions going on in alkylation. It can be with propylene and butylene. So C4 plus C3 gives C7, or C4 plus C4 gives C8. Isooctane, your basic 100-octane fuel, reference fuel. And when you do it with propylene, you'll get isoheptane. Remember, normal heptane was 0. And this is one hell of a lot higher, probably 90 or something. So just by isomerizing, you gained a whole lot of octane. So, see, the olefin, the way the reaction goes, olefins are very reactive because this double bond will break very easily and allows it to combine with things. That's why you make polymers out of olefins. Polyethylene, polypropylene, polybutylene. That double bond, it makes it a little more reactive. So another reason they don't want it in gasoline is because it also reacts in the atmosphere. So, but anyway, it's very useful chemical property here in this alkylation process. It allows these two to go together. They wouldn't otherwise. They wouldn't react at all without that double bond. So, same here for C7. So, anyway, that's basically. And people want more and more alkylate, being the desired gasoline. So, Chevron's even recovering the C5 olefin and reacting it with isobutane, and that, of course, would make a C9, I guess, isononane or something, or nonane or something like that. So, yeah, they're even doing that. So, there's the chemistry anyway. And let's see, back to that one. Okay. And we'll expand. All right. Okay. Yeah, and we'll expand that all the way. Okay. As I mentioned, butylene is the preferred feedstock for making alkylate. This gives a little example of some of the feeds that come into the alkylation unit. FCC, as I mentioned, is a better feed, higher in butylene and higher in iso too, which is one of the reactants. And so that's an all butylene feed. Now here's the kind of product quality you'll get out of it: octane of 96 and a motor of 94. Actually, that's an interesting property of alkylate. Most of your gasolines will have a difference between research and motor of 5 to 10. Alkylate's much smaller. Now, the way we rate our gasoline in the U.S. is R plus M over 2, the average between these two. So alkylate has another advantage in that the motor is much higher, so your average R plus M over 2 ends up pretty high. With reformate, that difference is 8 or 10 numbers. So another advantage of alkylate, higher motor octane. But see, if you have some propylene in there, that lowers the octane a little bit. So, all right, now let's see product yield. So you also, with all butylene feed, you got another couple percent total liquid yield. So that's worth something. And your acid consumption was half as much with all butylene. So, and that being a major cost. Okay, what's the next one here? Okay, what do we got here? All right, now we'll get into even more specifically on the butylenes. Some are better than others. So we prefer butylene over propylene, and then the higher you get in carbon number, you go C4, C5, C6, the more isomers you create, the more possibilities of how those carbons and hydrogens can combine. So whereas propylene, you just had one olefin. Well, now you go to C4, you've got 4 or 5 of them, or 3 here at least, and one of these has a cis and a trans, which you chemical guys will remember that maybe. So, and as you go up in carbon number, you get more and more isomers, and finally the chemistry is impossible. You don't even bother trying to describe it anymore. You just give it bulk properties. And so, but at least down here at C4, you can still describe the chemistry. So, okay, just comparing them. 1 butene, 2 butene. And I think 2 has a cis and a trans, but I didn't get to that detail. And isobutylene. Let's compare how they do. Percent TMPs, that's the desirable product, trimethylpentane. And as you can see, 2 had the highest percentage of both. Many more of these in the product and many more ICHs. So then, not surprisingly, the octane was much higher. As you can see, another 14 there and 3 or 4 there. So definitely would like to do this. And somebody made a process to take this mixture and maximize the amount of this. So, okay, that's, all right. Now I think the next one was, what did I say? Okay, we're going to go to that slide, which is, we'll look at the process that does this now. Let's see, hydroisom, okay. Yeah, there we go. Okay, we're going to maximize 2-butene, and here's what happens when you use that process. And Chevron has 2 of them. They have one on their C4 stream and one on their C5 stream called selective hydrogenation. And so, let's see, what does it do? Okay, there's an example there, butylene. Wait a minute here. Oh, okay, now there's a significant thing there. That's butadiene. Now, whereas butylenes are good, butadiene has 2 double bonds in it. And it's even more active and polymerizes even easier than butadiene. In fact, that's rubber. Most rubber is made from butadiene rubber. And see here, when you put it through this process, it not only maximizes this 2-butene, but it also knocks down the butadiene from 8,900 ppm to less than 100. Now, the reason that's important is butadiene reacts with the acid catalyst and forms more sludge, so increases your acid cost. So this process, in addition to maximizing 2-butene, also minimizes butadiene. Okay, let's look at the butylenes. Okay, what it did, but it reduced the 1-butene. It increased the 2-butene, which is the one we want, and even increased the iso. So it got rid of the 1-butene, which is the one that had the lowest octane. So it helps your feed out quite a bit. And let's see, iso. Down here is that iso. Oh, isobutylene. What did it do to that? It knocked that down too. So maximize 2-butene. What does it do to iso? Well, it increased the isobutane. Well, that's pretty much equal there. Acid consumption went less than half, so that saved you some money. Octane went up, well, about a point. Average product. This thing didn't focus very well. It can do better. I think that's a little better, yeah. Okay, so actual alkylate went up pretty much significant amount, 700, so 15-20%. And these numbers got off, but all right, then credits. Okay, so here's how much money this made for you. This costs money, and you have to operate this unit. But here's what it did for you. Acid credit, 70 a ton. That was $500,000. Butane credit. Okay, I guess it made more. Made less butane. Octane credit, another 163. So all in all, it looked like it picked up, 700,000 a year. So, and obviously you'd balance that with the cost to put this unit in and see how it paid out. So these are kind of some old figures, but nevertheless, that's another process that's carried on here. Okay. What's next after this? Okay, we'll get into this acid consumption. And I'm concentrating on sulfuric here, because that's what we're working on now, but HF has some advantages, and we'll get into that in a minute.
Can you expand it?
Oh, yeah, I'm sorry, sure. Yeah, I definitely have trouble myself, too. So in this case, it's sulfuric. Now, one advantage of sulfuric over HF, it's much less volatile. I don't know if you've seen sulfuric, but if you've been in the chem lab, you might have seen it. It's pretty heavy stuff. Used to call it oleic acid, I guess, because it's oily. And anyway, so one advantage is it doesn't vaporize and put any pollutants out. And although you certainly don't want it on you, that's for sure. But it's not as bad as HF. HF is, I don't know if you know what the problems are with HF, but HF goes right through your skin, right to your bone. It wants calcium, and if you get a drop on you, within less than a minute, it'll be on your bone eating the calcium. So, wicked stuff. Sulfuric is yeah, it burns, no doubt about it, but doesn't go in and cause internal damage like HF does. But anyway, so it's been the standard process, but HF has taken over, and there's some advantages to HF. Normal acid consumption, 0.3 to a pound of acid per gallon, and that many tons a day. That's quite a bit, isn't it? $80 a ton. We're talking millions a year in just acid consumption. So, and certain contaminants consume acid, and you'll try to eliminate them in the feed. Ethylene, you'll try to get that out of the feed. So that means back at the cat plant, let's see, you had a deethanizer and a depropanizer. The deethanizer was supposed to take all the ethylene out before you went to the depropanizer, so that would tell you operate that unit very well and keep the ethylene out of the propylene. So, because that's going to eat up acid, could be 500,000 a year. And butadiene, that's the real bad one that I mentioned. That hydroisomerization process helped remove that, because another $1 million a year there, typically from butadiene. So, sulfur, you have to desulfurize the feed very, very well, because that'll chew up some acid. So typically the olefin stream coming in will be Mirox treated, which is a caustic process that will remove the mercaptans from the butylene stream. And even water, you don't want any water in there, so they'll dry the feed to an alky plant. And altogether, it's a couple million a year due to these contaminants, and based on a 10,000 plant. So, okay, there'll be similar figures for an HF plant, but the consumption of HF is a bit lower, is a fair amount lower. So, okay, what do we got next here? Let me go back here and make sure I don't have a switch to make. Okay, before this, okay then. Yeah, now let's see here, I guess. You go to portrait here now. Let's see how do I do that. Yours is in portrait, the copy you have. Let's make this one in portrait so we can read it all. All right, now we'll do this. Okay, so comparing HF and sulfuric. These figures aren't totally up to date by any means, but similar number of plants in U.S., more barrels a day are in sulfuric. By now, HF may have caught up because most of the new ones have been HF. And UOP licensed most of the HF, but there's some other processes too. Phillips, for one, and some others. And Stratco does most of the sulfuric ones. They're a small outfit in Kansas City. And Chevron's right in cooperation with them now are doing some new cutting edge technology they may install there at El Segundo. So anyway, operating temperature is the major difference. Now, being 40 to 50 degrees, you've got to have refrigeration to get down that low. And HF, on the other hand, can be 90 to 100, so you can pretty much do that without refrigeration, typically. And probably the lower the better, too, as far as thermodynamics. So capital relative to install the plant, sulfuric would cost a little more. Operating cost, pretty close on butylene, which is your preferred stock. Propylene, I guess sulfuric costs definitely go. I think because acid consumption goes up, and the consumption see much lower on HF.